Please listen carefully.
Hello and welcome to GasGasGas, your one-stop podcast for the FRCA primary exam. This podcast will fill your brain with information. Listen to it, think about it, and check out the show notes on the website. There you will find the core diagrams you need to be able to draw and describe for the exam. This podcast can squeeze into your day. Listen while you're driving to work, cooking dinner, maybe when you're on call, or in the gym. Eventually the revision is going to end. But for now, expect facts, concepts, model answers, and the odd tangent. Remember to rate and follow the show to hear much more. Hello, my fellow GasGasGas compatriots. This episode is looking at how you go about comparing and contrasting volatile anaesthetic agents. Why do we bother? Because in the exam, they like to test your ability to weigh things up and compare because it demonstrates you understand the differences. We're going to look at the comparisons between blood gas partition coefficient, oil gas partition coefficient, the boiling points of the various agents and why that's important, and the saturated vapour pressures of the various agents, and a brief jaunt into what that is. There's going to be a future podcast on all these things in more detail. We're also going to include the global warming potentials of these various gases, touch on what that actually means in real life, as well as the particulars that the patient may experience that's different between these agents. So broadly speaking, a volatile anaesthetic agent anaesthetises you, and they generally have all about the same side effects to varying degrees. So they all tend to drop your blood pressure to some degree, except for maybe desflurane. Some of them are more capable of potentiating arrhythmias, like halothane, not that we use that much anymore. Almost all of them, to a degree, obtund your response to CO2 in your plasma / in your brainstem. And they all inhibit hypoxic pulmonary vasoconstriction, so they're going to make shunts worse. Unfortunately, they're all bronchodilators to some degree. From a CNS perspective, they cause general anaesthesia, they all increase cerebral blood flow, and all reduce the metabolic requirements of your neurons in your brain. Touching on increased cerebral blood flow, this relates to intracranial pressure. SIVO is the least bad, and desflurane is probably the most bad from a raising ICP perspective, and they all make you a bit sick. They all tend to reduce renal blood flow. That might be in part just because they drop your blood pressure a bit. They all cause uterine relaxation. This is really important when you've just GA'd someone for their major obstetric hemorrhage and you've had to wang in some SIVO with relative gusto, and actually you're going to make the bleeding worse, which is unfortunate, isn't it? From a muscle perspective, they all potentiate neuromuscular blockade and probably in their own way reduce skeletal muscle tone, and they all can trigger malignant hyperthermia. So before we get into the nitty-gritty of who does what, where and when, I just want to go over a few of the points that we're comparing. So what on earth is saturated vapour pressure? This melted my brain when I first had to try and think about it. Ultimately, it is a theoretical point where a liquid has reached an equilibrium with the gas space above it. And when I say an equilibrium, in that some of that liquid is evaporating into that gas space, and some of that vapour is recondensing back into that liquid space. If there's no vapour in that gas space to start with, quite a lot vapourises. Once it starts to fill up and gets a bit full, the rate of fill versus condensation balances out again. That's the saturated vapour pressure, which is going to be the partial pressure exerted by that vapour in that gas above that liquid. This is a big deal because that's how vaporizers work. They vaporize. Now, SVP is particular to a temperature and is presumed to be at standard pressure. The things that influence SVP are the colligative properties of the liquid, something we'll go into in the future. But if you imagine, if you add a solute to a liquid, like maybe salt into water, it alters the properties of the water. And that's what we're talking from a colligative property perspective. Another important term is boiling point. This is the temperature at which the vapour pressure of the liquid equals the pressure around the liquid, so that throughout the liquid, as opposed to just at the top with evaporation, that liquid wants to become a vapour. That's why you get bubbles coming up from the bottom of your kettle, not just on the top. It is standardised to 1 atmosphere of pressure. Why is it standardised to 1 atmosphere of pressure? Well, if you drop the pressure, then things will boil more easily because the energy taken to reach that equilibrium point between the vapour pressure and the atmospheric pressure will be lower. That's why water boils at a lower temperature on Everest. And just for clarity and specificity, evaporation is the shift to a vapour phase that occurs below boiling point, generally at the surface of a liquid or at the liquid's interface with another material, i.e. the bubbles that form on the sides of your glass, even when it's just still water from the tap. Last one to mention is, what is global warming potential as a number applied to a thing? So this is a relative potential for greenhouse gas effect as a comparative ratio sort of thing to carbon dioxide. So if you take an example, our joyous friend nitrous oxide has a global warming potential of 298. That means if you chuck 1 million metric tons of nitrous into the atmosphere, you would need to chuck the equivalent of 298 million metric tons of CO2 to cause the same effect. So you can see that nitrous, 298 times more greenhousey. GWP, unless specified otherwise, tends to reflect 100 years of time. CO2 hangs around for a very long time in the atmosphere, i.e. thousands. Nitrous, well, we'll check that out in a mo. So we've done our define or die, talking about saturated vapour pressure, boiling point, and those other bits and pieces. And now on to my latest fun descriptor, compare or cry. I mentioned earlier that examiners like to ask compare-contrast questions because it demonstrates to the examiner that you have a good nuanced understanding of the differences and the different choices you could make for your patient. Now, I'm openly going to say here, guys, that it's quite hard to do this well and slickly because there's lots of variables to consider and you might find yourself meandering, and I'm desperately going to try and not meander. Therefore, I am going to focus on isoflurane, sevoflurane and desflurane. But if you check out the show notes, I've gotten overexcited, and I've also included halothane and ether, and I've also mentioned nitrous oxide, which I'm going to mention in passing here.
So, Doctor, could you compare and contrast for me the properties of sevoflurane, isoflurane and desflurane and their pertinent relevant effects and side effects for the patient?
I'm going to compare sevoflurane, which is an agent I most commonly reach for, against isoflurane and desflurane. So the MAC in air or oxygen of sevoflurane is 2% end tidal, compared to the much higher MAC in desflurane of 6.6% and the lower MAC in isoflurane of 1.2%. Thinking about how these agents onset and offset in patients, I consider the blood gas partition coefficient. In sevoflurane, that is 0.69, which is relatively low comparing it to all the other volatile agents. Desflurane is a jot lower at 0.45, whereas isoflurane is a fair bit higher than the 0.69 of sevoflurane at 1.4. So isoflurane is considered the most soluble in blood of these three agents. That makes me think that isoflurane's onset time is a bit longer compared to both sevoflurane and desflurane, and that arguably desflurane's onset time would be considered the fastest, albeit though it requires a higher MAC of 6.6% to get there. Thinking about the potency of these agents, the oil-gas partition coefficient is the most relevant. A higher number generally being considered a more potent agent, i.e. a more lipid-soluble agent. Sevoflurane has a oil-gas partition coefficient of 47. This is compared against isoflurane's 97, i.e. it's more potent, hence the lower MAC of isoflurane. Desflurane comes in at 29, which you would expect given that its MAC is 6.6, so you require more agent for the same effect. I'm going to think about here about the side effects of these various agents. Generally speaking, they all tend to lower MAP, cause bronchodilation, inhibit hypoxic pulmonary vasoconstriction, and tend to have an influence on cerebral blood flow, increasing it and raising intracranial pressure. Sevo being the least likely, and desflurane being the most likely to increase intracranial pressure. Of interesting note, desflurane tends to lower blood pressure the least, and sometimes induces a tachycardia.
Oh, that's very good, Doctor. Could you just briefly outline the saturated vapour pressures and boiling points of these three drugs?
Yes, of course. Sevoflurane has a saturated vapour pressure at 20 degrees of 22 kilopascals. Isoflurane saturated vapour pressure is 32 kilopascals and desflurane is 88.5 kilopascals at 20 degrees. This is of note when comparing the boiling points. Sevoflurane boils at 58 degrees, isoflurane at 48, but desflurane at 22.8 degrees, so practically at room temperature. The risk here is that in a standard vaporizer, desflurane might actually be boiling, depending on how warm the anaesthetic room or theatre is, and this might lead to disproportionate and unclear dosing of the patient, which would understandably be very dangerous. So the desflurane vaporizer is actually heated to avoid these complications.
Excellent. Just thinking about these drugs for gas inductions, how would you weigh those up?
Well, for gas induction, the most important things to consider, beyond the pharmacokinetic properties of the blood gas partition coefficient, is actually the tolerance of the patient to the gas. Because you can have the fastest drug in the world in onset, but if the patient won't breathe it in because it's very irritant, it's not going to be very helpful. So sevoflurane, out of these three drugs, is the most patient-tolerated. It is non-irritant, doesn't trigger coughing, especially if introduced at low concentrations to begin with.
Lovely. And another important patient factor is that of the global warming effects of the drugs we use and the impact anaesthesia has on the environment. How do these volatiles play out in their effects with greenhouse gases?
Yes, so this is a pertinent topic. Global warming potential, or GWP, is used as a metric to try and compare volatile anaesthetic agents. This is because it's sometimes hard to weigh these agents up compared to, for example, CO2, because they all have differing live times in the atmosphere. Desflurane is certainly the culprit for having the greatest greenhouse gas effect. There's a number called global warming potential, and for desflurane that's 2,540, compared with isoflurane's 510 and sevoflurane's 130. Arguably, on paper, a low-flow sevoflurane volatile anaesthetic is the best of those three choices, although it may bear out that Tiva has a lower environmental impact. So guys, well done for listening to me waffle on about all that. I've got all these numbers in front of me, but I did learn most of them for the exams using flashcards. I think that's probably more relevant for the exacting numbers in the SBAs, where you might having to be way up certain things compared to other things, versus the Viva. I think you certainly should know the max and probably the blood gas and oil gas partition coefficients. You could probably get away with pointing out that desflurane tends to boil at room temperature, and that's why it's important to have that in a different vaporizer. I think it would be pretty brutal if they started drilling you down and asking you what the saturated vapour pressure of X was, but they could, and I'm sure they have done in the past. So feel free to check out the show notes if you want to have a little laugh reading about ether and halothane. I think it's quite fun. Something to point out is halothane actually has a global warming potential of 47. It only hangs around in the atmosphere for a year. The rest hang around a bit longer than that. Nitrous, 114 years. Ether is flammable and boils at 35 degrees. It tends to cause explosions when it's also mixed with oxygen if there's any sparks. Ho ho ho. The other thing that might come up or may not come up is how much they're broken down in the body. So sevoflurane, 3 to 5% is defluorinated in the liver. Isoflurane is very minimally metabolized at 0.2, and desflurane is barely metabolized at 0.02%. Halothane, 20% metabolized by the liver, and obviously 1 in 5,000 chance of causing a hepatitis and fulminant badness. Ether, from a side effects perspective, caused hypersalivation, which is something I only just learned, and that's probably why they used to pre-med people with atropine, as well as the morphine. The morphine, because it's incredibly soluble in blood. The BG coefficient of ether is 12 compared to Sevo's 0.69. So it just take ages to work. You'd be there really bored. If you had a patient who wasn't Scooby-Dooed on morphine, probably they'd just get really annoyed, wouldn't they? Have a look at the show notes. I don't want to get carried away here. You can look at the show notes on my shiny new website that is almost entirely built. Cool, eh? But anyway, thank you very much for listening. You've been listening to Gas, Gas, Gas with me, James. Next episode, lucky number 13. If you found it useful or awful, please like and subscribe and rate the show. Definitely check out the show notes for those diagrams and the detail of this content. It is a bucket of content to get to grips with. Keep working at it, and you will get better, faster, and stronger. It is vital to keep your interest live for the science that we're covering and not overcook yourself. You will be amazed by what you know come exam day. Don't freak out. Keep studying.